Labguy here. Today we're going to take a second look at the Denson Electronics video monoscope that I obtained recently. Denson Electronics was an excellent electronics surplus store of the 1960s and most of the 1970s, operated by Al Denson. It was located in Rockville, Connecticut, and Denson sold anything you can think of that was video related. He had television cameras and parts and videotape recorders and switchers and light kits. Anything that came out of a junked television station or TV studio of the industrial and educational varieties on the East Coast starting in the mid-60s through the 70s. Al put out a weekly flyer and he published an annual catalog. I grew up in Red Bluff, California in my teen years, from the age 10 to 18. That's where I lived. And it's, to call it the boondocks is polite. So my source of electronics parts, we lived out in the country, was the city dump, the county dump, the refuse location, and it was about 1 mile from our house if you walked in a straight line, and about 5 miles if you took the road. So I had a big radio flyer wagon, and I would go over hill and dale in the 110-degree heat, that's Fahrenheit, and I would go to the dump and I would come back with huge television sets strapped to that wagon. It would take all day, and that was my source of electronics parts. Then I was given a Denson Electronics catalog, and he sold things for 50 cents on up to $5,000. And Al Denson was the man who made it possible for me to build the first 2 video cameras that I constructed while I was still in high school. The first one was a copy of a Dage Model 80, and it was all vacuum tubes. And the second one was the one in Radio Electronics magazine by Gary Davis. That was a solid state camera using germanium transistors. But I digress. So that's Denson Electronics. Al Denson was apparently a local character. Kind of like that guy in Red Bluff that people still probably murmur about to this day. Who knows whatever became of that kid. So, anyways, the monoscope. It's based on the 1698 tube, which is a CRT. It is a monoscope tube, and it contains a fixed pattern of characters. The modern equivalent of this would be a character generator read-only memory on a video card, say in a terminal, in a computer terminal. That's what produces the text characters, texts and digits on the screen. This tube has a limited character set, and let's look at a picture of that right now. As you can see, it contains 10 digits. It has a 0, 1 through 9, and then a series of special characters. These characters would be read out. The scanning inside this tube would only scan large enough to scan one character, and then its position of that scan could be moved around over each of those character locations by a computer, which was attached to a very early radar system, probably in the right around the 1960s. And that was what this tube was all about. Well, apparently in 1977, and I'm basing it on the fact that this flyer is number 779, and I think the first 2 digits were the year. So possibly the 9th flyer he put out in 1977. That's a pure speculation. So that dates this to no older than 1977. I obtained this this unit recently from my good friend Bob Rosenblum, and we traded some things. He collects old computers, and I had something he wanted that was of no use to me, and I traded it to him directly for this, and Bob got the better deal. So the Monoscope it uses 4 tubes. It has 4 vacuum tubes, not counting the Monoscope. There's a dual triode back here, which is the 2 scanning oscillators, horizontal and vertical, a video preamplifier tube, a video mid-amplifier tube, and the final triode is a dual triode. They're all dual triodes, 12 AT7s, for those who are curious. One triode is the sync combiner, which takes the pulses derived from the scanning tube, combines them together, and and adds them to the video coming from the 2 video amplifier tubes. It's very simple. The final triode drives the output jack on the back. You can't see it through my arm. So that's the essential configuration of this unit. Now, when I got it, I turned it on as is to see how it was. I did inspect it. I compared it to the schematic, and it is built exactly to the schematic for the most part. Because he didn't use, the fellow who built this didn't use the exact transformers, he has a different pair of transformers on here, so the power supply differs slightly, but it produces the voltages required. So that's not an issue at all. It's quite common when you build junk. So I turned the unit on, and this is what I saw. It's making a signal, but it's missing the vertical sync pulse. We're looking at it as it's outputting. I can change the vertical size, as you can see, and the vertical centering, but you'll note that the 506 is the top line of the text, and the 708, call it, is the bottom line of the text. And it's split across the middle. There's a glitch in the video that has an unknown origin that is being interpreted by the television as the vertical sync pulse. You can see that bar across the middle, the approximate middle, that is the unit's attempt to produce a vertical sync pulse. It is kind of present, but it's severely attenuated. It's not big enough to trigger the TV. The TV cannot see it. So let's look at the video waveform and see what we can see. Looking at the video waveform, we can see that it's mostly there. The pulses going up from the heavy line are the video pulses. The pulses coming down from the heavy line are the horizontal sync pulses. This is what's supposed to be the vertical sync region. Clearly that's not working right. And if you look right here, there's a little bright spot, which is a glitch. And we're going to have to find out where that glitch is coming from. That's what the TV thinks is vertical sync. The reason this waveform is synchronized on the oscilloscope, believe me, this oscilloscope has a TV trigger. It won't trigger to this stuff at all. This is not good sync. And so I'm in line lock. In an oscilloscope, line lock is where you synchronize the scan of the oscilloscope to the AC power line. Okay, it has a built-in tap in one of its power transformers that is used specifically to trigger the scope on 60 cycles, and it's used specifically to look for hum. And we can see there is some hum in this video that's standing still. See all of this? This should be flat, but it's not, and it's in time with the power line sine wave. So what are we going to do about this? Looking at the input of the sync combiner, we're looking at the horizontal sync, and we'll spread this out so that we can see the individual sync pulses, and we'll trigger on them. These are the horizontal sync pulses coming from the horizontal oscillator. Yes, this is not a very good sync system. However, that pulse is as clean as a hound's tooth, and we are looking at 50 volts per division. That pulse is pulsing negative from 0 volts to about 80 to 90 volts negative. Next, I looked at the incoming pulse from the vertical oscillator. Can you see it? Can you see it? It's right there. Now the sync combiner should have the same level of vertical sync pulse as horizontal sync pulse. This vertical sync pulse is extremely low, and in fact turns out to be about 5 volts peak to peak, 5 volts negative. Again, that is an extremely ugly pulse, but it's not the right value. So let's look at the schematic. When we look at the schematic right here, that is the resistor that develops the voltage for the vertical sync pulse being tapped off of the plate of V4A on pin 6. They're tapping off the vertical ramp waveform, and when the vertical ramp goes negative, the sharp edge, it's AC coupled into this 560 ohm resistor. From there, it travels to a 4700 ohm resistor and a 0.1 cap, which removes any high frequencies that are present. The first filter, the capacitor and resistor, were responsible for coupling the sharp edge of the signal and blocking most of the scan signal. But you can see some of the scan is in there. No big deal. And then from there, it went through a 4700 ohm resistor and a 0.1 capacitor and a 6.8K resistor, which the user, the guy who built this, had changed, trying to make that pulse bigger at the junction of what was originally two 15K resistors going into the grid of V3B. Note that V3B's grid is clamped to ground by a germanium diode, a 1N34A. Okay, so the horizontal sync at the top of the 15K resistor, where the 0.002 capacitor is, was 50 volts peak to peak. The voltage of our vertical sync pulse at the junction of the 4700 ohm resistor and the 0.1 is 5 volts peak to peak. It suddenly occurred to me, looking at this circuit, that we have resistors in the 15,000 ohm range, 5,000 ohm range, and suddenly one of them is 560. This is off by a factor of 10 times. It's actually, the 560 resistor is incorrect. It's the wrong value. There's a 0 missing there. That is supposed to be a 5.6K resistor. Let's change that. All right, now that's what I call a vertical sync pulse. Not really. So it is now 5, 10, 15, 20, 30, 35 volts or so. Much bigger. It's much bigger. And you can see in the video signal that this monstrosity right here, that's now good enough to be a vertical sync pulse for that time period. Let me be clear, this is not a Tektronix quality instrument. We have a circuit here that's simpler than a 5-tube table radio. There are only 4 tubes in this system. the fact that it makes video is an amazing thing. Let's look at the picture. Woohoo! Much better. Much better. The television is now synchronized correctly, and we can see our tube using our vertical centering control. We can move up and down and left and right. Our vertical size control works, and our horizontal size control works, but we don't want to mess with that too much. The horizontal size control also affects the frequency. So this is our scanning frequency here. We can play with that, but we're right on at that point. And now there's a new problem. Can you see it? On the third line of the text, you can see that rip across the picture. Now what the hell is that? Well, I looked at the video amplifiers with the oscilloscope, and you can see the step in the video. It's quite apparent, and it took me a while to find the source, and what that is the AC sine wave in the heater supply to the tubes is crossing zero at that moment. Now the fellow who built this did a good job of wiring the 12AT7's heaters. He wired them in their 12 volt mode. A note about the 12AT7, it's a dual triode that has a 6 volt heater in each triode. They're connected in series within the tube, and 3 pins are used. So there's call it a center tapped heater, if you will. So there's the 2 outside connections and the mid connection. The 12AT7 heater can be wired either with the 2 little heaters in parallel for 6 volt operation or in series for 12 volt. Our builder has decided to wire in 12 volts because his transformer has 12 volt output. And the wiring of those is done properly using twisted wire, but for some oddball reason, from the originating point, he ran 2 pairs of twisted wires to different tubes. I don't know why he didn't run a single run of twisted wire. And when he split that run, he's got 2 different run lengths, and more than likely the phase of the heaters in different tubes are in different positions. You get this rip across the picture. What I discovered when I went to connect the oscilloscope to the 12 volt winding of the power transformer to have a look, this is what I saw happen. The picture cleared right up. So the floating filaments, not referenced to the ground of the system, was the problem. So that has repaired all of the major problems, the functional problems. The fact that we're picking up noise is because the monoscope tube is hanging out in open air, in open space. And I'm willing to bet that some of that interference you see in the picture is AM radio stations. I'm just guessing. Sometimes it gets quite noticeable and flashy. I don't have an AM radio, or we'd try to see which stations that is, because you would see it pulsating to the speaker of the person speaking or the music playing. Of course, music on YouTube, you know. So there you go. I'm declaring at this moment that the Denson Monoscope is fully functional as designed. So there is the final version of the video. You can see some slight AC hum bars, which are probably being picked up directly by the tube. Notice what happens when I place my hand near the business end of the tube. We get interference being coupled in. And one more thing, I discovered the source of some of the noise in the video, and it is my video lights. When I turn these on, these are compact fluorescent lamps. They put out quite a bit of interference. Turn it off, interference gone. So the interference in the image that you see is external to the monoscope. The monoscope, I declare, is operational. this concludes the initial operation of the Denson Electronics Monoscope. I hope you found this video entertaining and informative. Thank you for watching. I'd like to welcome all of the new subscribers. We keep getting more. I must be doing something just a little bit right. Thank you. Thank you very much. Greetings to all of my regular subscribers. Thank you for watching these videos. Without you, I would be talking to myself. No, you wouldn't. Yes, I would. No, you wouldn't. It's always butting in. So anyways, I have more projects coming up, and all related to vintage video of the 1950s, 60s, and 70s. Back before the no-brainers. That's what I call camcorders. Back when you had to really have some skills to keep that stuff working to make really mediocre product. So with that, until next time, Labguy out.